Hi everyone, last packet, well, last official packet. If you're actually interested in undergraduate research next semester, I will put up a quick video after this one at some point in the week. Okay, so if something you're interested in, take a look. If not, not an issue. Okay, this is the last packet otherwise. Okay, so what we're going to talk about is something different, right? So we haven't talked about intermolecular forces yet. Okay, now to understand what that word means, we have to do an analogy, right? So here's an analogy, right? So I'm going to draw you a very bad diagram, right? So you tell me what this is. That's a very bad picture of the United States. That's where we are, right? Okay, this is not to scale. What's this? That's England, right? There's London, there's Liverpool. That's where I'm from. Okay, now let's say you're traveling to England, right? Okay. What terminal do you go to? What terminal do you go to at O'Hare? You go to the international, right? So inter literally means international, between, inter means between nations, right? So international, between nations. Sometimes we call 55 an interstate, right? Because it goes between states, yeah. So inter means between. Right, so inter, we'll come onto it down here in a moment, right? Inter means between, right? Fair enough. Now, this summer, next week, right? I might be flying out to Montana, right? Never know, right? Okay, got cut off there, right? So if I was going on vacation to Montana and I was flying out of O'Hare, I'd probably go to Terminal 1, right? But if we're talking scientifically, it would be called the intra, right? Intra-national, because that means within, right? So intra means within, inter means between, all right? So we've talked about intramolecular forces this whole time. That's a covalent bond, it's a polar covalent bond, that's an ionic bond, okay? So intra, within a molecule, within a compound, within an element, inside that thing, right? Inside the molecule, there's intramolecular forces, right? So they're forces between atoms, all right? Chemical bonds, okay? So intramolecular forces, forces inside a molecule, are essentially bonds holding one atom to another. An H connects to an O, connects to an H. That's bonds connecting atoms in water, right? And in the big scheme of things, they're very strong. Pick a number. We had that table of bond enthalpies, you know, something in the 300 to 400 range, right? Okay, so intramolecular forces, regular chemical bonds, strong, right? Okay, now if you think about it, in ice and in liquid water, why aren't those things in the gas phase? Because there must be some weaker force holding one molecule to the next, right? That's called between molecules, right? Okay, so intermolecular, right? So intra is within a molecule, inter is between, okay? So it's a force we haven't seen yet. It's got to be in a liquid or a solid, right? So, you know, ice is a molecular solid, right? What's one molecule of H2O doing? It's holding onto the other with an intermolecular force or bond, right? And these are generally pretty weak. They're in the 2 to 50 kilojoules per mole range. All right, now that makes sense because when you boil water, what do you get? You get steam, which is just H2O molecules, I'll say, just further spaced, right? So when I go from here to here, I just break the intermolecular force, right? So there's a weak force between molecules in a solid, ice, liquid water, which then are completely gone in steam, yeah? And of course, when you boil water, you get steam, you get molecules of H2O just further spaced apart, right? So that makes sense because the weaker bond between the molecules broke first, not the stronger bonds holding the atoms together inside a molecule. So you don't get a bunch of hydrogen and oxygen atoms when you boil water, right? You just get steam. Okay, so there's an example. Now remember, in the last packet we kind of touched on this, you know, again, as we've done before several times. All right, so if I kind of look at two water molecules in a glass of water, there they are. That's the intermolecular force holding one molecule to the next. And it's kind of long, right? It's kind of long because it's kind of weak, yeah? Okay, but within a molecule, the bonds are shorter, so they're stronger. So, you know, an average covalent bond, probably 96, 100 picometers, something like that. 3 times longer between molecules. Okay, so there we go. All right, so that explains the strength of these intermolecular forces. Okay, we haven't talked about their nature yet, you know, what they're actually made from, but we'll get onto it. But they're longer and they're weaker bonds than what we've seen already inside molecules. That's the key take home. All right, now, so I guess we're obeying the longer equals weaker idea, right? Now, if you think about it, the strength of the bond between molecules, the intermolecular force, really helps define their melting and boiling point, right? So if you think about it, if I got two H2Os stuck together in a block of ice, right? Ice is rigid, so that bond is quite strong, yeah? Okay, and then if I take my ice and I heat it up, and I use Kelvin because it sounds more, right? So if I get the ice up to 273 Kelvin, I have just enough energy to snap that bond I see in ice, yeah? But it doesn't really snap it, it kind of weakens it, and then the molecules can tumble over each other. They've got a weaker bond, they're hanging on, but they're not as tightly held. They're a liquid, right? Then I take my liquid up to 373, 100 degrees C, that last bond is broken and the molecules just fly off into the gas phase, yeah? So if I think about it, the stronger those bonds are, those intermolecular forces, the higher the melting and boiling points are, okay? So it's a good rule of thumb. If I have a strong intermolecular force, I have a high melting point or a high boiling point or both, right? Okay, so kind of a key fact here, right? So the intermolecular forces are what hold molecular materials together in the solid and liquid phase, right? It's what holds one molecule to the next, right? Okay, in a snowflake or something, right? Or an ice cube, something like that, right? Okay, and then those intermolecular forces are broken when we see a change of state, right? So when ice turns to liquid, water turns to steam, we progressively kind of weaken and break those bonds, right? Okay, and that's kind of shown pictorially here with a really, really nice kind of energy diagram, right? So here I have, you know, imagine you're taking an ice cube out of your freezer at minus 25 degrees C, right? That's what it's not such a great picture, but you can just about make out the individual water molecules, right? The individual water molecules are actually touching, but they're kind of in these hexagons. That's why a snowflake has hexagonal symmetry, right? Because it's kind of this touching molecules, right? But then they have this kind of open structure, if that makes sense. It's like a bunch of people holding hands in a circle. Yeah, everybody's touching everybody. You can't get any closer, but then you have this kind of space kind of in the middle of the circle. All right, that's what we see there, and that's why ice floats. Ice is less dense than water because it's got these kind of gaps, right? So the gaps don't weigh anything. Ice is less dense than water. All right, so below 0 degrees C, that's what ice looks like, right? Okay, and then we kind of, you know, raise the temperature, increase the heat added, if you like, okay? And we see, you know, what happens when you add heat. So it's like getting a Bunsen burner to an ice cube, yeah? So you start adding heat, and of course the temperature of the ice cube goes up. Fair enough, right? And then you get to 0 degrees C and think, oh, it melts. Well, yes, it does, but it's interesting. The temperature when the ice is melting stays constant for a while, and that's called heat of fusion, okay? I'll put it there, delta HF, right? That is interesting. So the energy is not being used at that point to make the molecules move faster. It's being used to snap the bonds, right? So the energy of motion doesn't change, so the temperature doesn't change, right? So it stays at 0 for a while because the energy is being used to snap these bonds, turn solid into liquid, right? So this is happening right here, okay? So, you know, we've got a little bit of ice there, we've got some liquid. So that's kind of the intermediate. So that's happening in this region 2 here, okay? Take a closer look at that. I mean, you can't really see it necessarily on the screen in front of you, but you've got the paper. Yeah, okay, take a look. Then once we've all melted, now we've got water at 0 degrees. So you can have ice and water at 0 degrees C, right? Okay, if we keep adding heat, it'll eventually turn all to liquid at this point, yeah? And once it's all liquid, there's no ice left, there's no bonds in, if you like, the solid phase of H2O, right? Then the temperature will start to rise again as we keep adding heat. We're gonna, you know, it's like we're boiling water for a cup of tea, right? Temperature goes up until we get to the boiling point. Boiling point of water, remember, the liquid is a drop, right? So it's not all spread out, it's in a drop. So the molecules of water are bound to each other just more weakly because they can tumble over, but they've got to remain in contact. Because they remain in contact, they're bonded, right? Slightly more weakly than the solid, but hey, they're still bonded. What happens while they start going into the gas phase? So we're breaking the bonds between the water molecules to liberate the molecules into the gas phase, right? And that happens here. So here, you can see it kind of takes more energy to do that because the plateau region is longer here, right? Okay, that's called the heat of vaporization. If you remember our examples, we actually looked at the heat of vaporization of water with heats of formation, okay, and CS2 as well we looked at, okay? So that's what's actually happening during the heat of vaporization. We're taking the liquid at its boiling point to the gas at its boiling point, and we're breaking those final bonds. And then, hey, if I got the gas, it just gets hotter and hotter and hotter. Okay, there we go. So you may see that on your future work, okay, as on a test, okay, or if I got the other one, you may see kind of the, oh, it's the same. There's another one, the generic one, right? What I was going to say was you might see the cooling curve, right, which would be kind of kind of like that, okay? So you get a heating curve where you start from a low temperature and go higher, or you can kind of run it backwards, cooling curve from a high temperature and go lower. But remember, there will be two plateau regions when you're changing state. Heat of vaporization, liquid to gas. Heat of fusion, they call it, solid to liquid, okay? So if I was able to work out, hey, how many kilojoules per minute kind of thing, and work out that distance in minutes, I could work out how many kilojoules I needed to kind of turn it from a solid to a liquid. Similar here, work out the number of kilojoules to turn it from a liquid to a gas, and that's heat of vaporization. That's what we did already with our heats of formation in the thermo packet, but here is like an experiment to do the same thing. Okay. All right, moving on. All right, now, we haven't talked about the nature of these intermolecular forces, right? We talked about intra, right? Covalent, ionic, polar covalent, right? But we haven't talked about the very nature of the bonds between molecules, right? Because they're not sharing electrons, right? They're not, because that's a short range effect, right? This is a long range effect. So how does it work? Well, it turns out there's three different kinds of intermolecular force, right? Okay, the first one goes by many names, right? Some people call it van der Waal or just VDE, right? Van der Waal, Van der Waal, right? Okay, which is an old name, to be honest, so you probably won't see that, Van der Waal. Van der Waal, Dutch, VDW, WAAL, I've just remembered. Okay, Van der Waal. That's an old name. We tend to call them these days London dispersion forces, but I prefer the more descriptive name, which we'll get to in a second, induced dipole-dipole bonding. Okay, now it turns out that every atom and every molecule in nature can do induced dipole-dipole bonding, right? And as we'll see later, it really depends on how many electrons the atom or molecule has, and every atom or molecule has electrons. And, you know, the strength scales with the number of electrons, which we'll see. So it starts really, really, really weak for helium and hydrogen, things like that, but it gets pretty strong for things like, you know, big macromolecules like proteins, right? Okay, so it varies from weak to strong depending on the size of the molecule in question, but everything does it because everything has electrons, right? So there's a variation in strength from super weak to really quite strong, and it's there for all molecular material. So consider it like an entry-level bonding. Everybody has it to some degree, right? Okay. Now the next strongest form, and generally speaking, this one's stronger than this one. So the next one is dipole-dipole. We've seen a dipole already. So molecules with dipoles, we saw HCl in the last packet, right? So HCl, because of that polar covalent bond, has a plus end and a minus end. Hey, plus end of one can attract minus end of the other. So that's a permanent dipole-dipole attraction, right? So only works for polar molecules, and this is on top of the underlying induced dipole-dipole, right? okay? Now, if you're taking a biology course or even a organic chemistry course, you're probably familiar with this term hydrogen bonding. Okay, hydrogen bonding is called its own special thing in biology, but in chemistry it's just a very, very strong dipole-dipole force, but we go with it and we'd say, hey, it's a different kind, right? So really it's just a super strong version of dipole-dipole, but it is very prevalent in organic systems, natural systems, right? So it's kind of a special case and we treat it as such. So hydrogen bonding is super strong. It's about 10% the strength of a regular covalent bond, but it's only for very, very specific molecules, right? And if you ever wondered why certain atoms are used to make natural materials, it's because those things need to hydrogen bond, all right? So the structure of, for example, DNA wouldn't be a helix unless there were hydrogen bonds inside it, right? Our cells wouldn't work unless there were hydrogen bonds inside. So natural materials like plants, humans, animals, right? We all need, on the microscopic level, hydrogen bonds for our cells to work, right? Okay. All right, so now let's look at the first one. We'll take them in order. Okay, take them in order. First one we'll do is the induced dipole-dipole bonding, right? And there's a picture here, I got it from the textbook. But what I'm going to do, I'll actually draw you a better picture, right? And I will put this in the notes, okay? So it kind of really kind of pays to think about this in terms of like a progression in time, right? So here we go, right? So we're looking at the liquefaction of helium. Helium is the thing with the lowest boiling point, right? Okay, so that means it's got the weakest intermolecular force. If we understand the weakest one, we're at a good place, right? So imagine helium at about 5 Kelvin, right? There's helium. Now helium has a +2 nucleus, right? There's the nucleus. And it has 2 electrons in that 1s moving around real fast. So they're in there somewhere, right? Okay, so that's my helium. I'll just write He for helium, all right? Now, near its liquefaction point, boiling point, right? Condensation point, whatever you want to call it. Other heliums are moving around and occasionally they bump into each other, right, and bounce off. But because it's down at 5 Kelvin, they're moving super slow, which is kind of important, right? Now, this is what happens. So imagine, just for a split second, 2 helium atoms, both in the gas phase at 5 Kelvin, and they're about to form a liquid. They're about to kind of form a bond, right? An intermolecular bond, right? So how does one helium stick to the other? Interesting question. Now, remember these electrons, I've drawn them like that, right? But they're really moving around at close to the speed of light, yeah? So they're in there, buzzing around super fast, yeah? They're here, there, yeah. Just for a split second, let's say they're over here, right? Just for one split second, they're on this side of the atom. Fair enough, right? So let's kind of say now they're there, yeah? Okay. Now think about that. That means, if you like, the electrons are on this side, so that makes that side of the atom a little bit minus. And if you like, on the other side where the nucleus is, it's a little bit plus. We're having come into existence a time-dependent dipole, right? Remember dipoles? It's not permanent, right? They're flipping into existence. It might be this way, might be this way, might be this way, all the time, right? It just for a split second, it's minus this side plus that side. Fair enough, right? Now, I have to tell you a story from when I was younger, right? When I was younger, I used to watch Channel 4 really late on a kind of a Monday night, right? Okay. And in the 1980s, Channel 4, and there were only 4 TV stations at the time, Channel 4 was the 4th one, okay? They showed American football, and I was obsessed with American football, right? I used to watch the San Francisco 49ers, because in the day, the 1980s, they were really good, right? Okay. And I had to learn the rules of American football as an English person watching, right? Once a week, late at night on a Monday. And eventually, you know, just based on watching the game, I eventually figured out most of the rules, right? Okay. However, the last rule I learned, right, which was kind of the hardest rule to learn for me, was being induced offside, right? How does the offense induce an offside in the defense, right? Have you seen that? All right, so let me just go over here real quick. So here's the defensive line, here's the offensive line, there's the quarterback, right? There's the linebackers. They do what's called a hard count, right? Okay, so the quarterback will kind of kid the defense to think he's going to throw the ball or something, pass it or whatever, right? By doing a hard count, right? And then, you know, they think, that he's about to throw the ball. So they go early, right? So they go early. They were induced offside, right? The fact that he winked, he kind of did a hard count, induced them to cross the line, go offside, and he gets the ball, throws it on the ground, it's a penalty. They get 5 yards, whatever it is, right? So hopefully you're more familiar with the being induced offside than me, but that's what I understand to be that rule, right? Thank you, John Madden. Right? Now think about that, induction, right? So induction is making a neighbor do something, right? Okay. So if I if I give someone a funny look, right, maybe they wander off, right? That's a bad example, but you get the idea, right? Okay. So, act all crazy on the L and people will move away from you. That's induction. Right? So look here, though. Look here, right? So here are my 2 electrons, just for a split second over here. When these electrons look over, what do they see? They see a big old wall of negative charge, right? And what do? Well, they're repelled by that. They're induced to move over here. Okay, so they're induced to move over there. And they themselves set up their own equal and opposite dipole in the neighboring atom. Okay, so these electrons scared these ones over here. They induced them, right? Okay, then these will induce the next one, the next ones, and the next ones. Okay, now think about that. This side of the atom's a little bit plus. This side's a little bit minus. Oh, a plus attracts minus. So if you want to think about it like a super weak ionic bond, you maybe can, right? Because it's a plus-minus interaction. Fair enough, right? And that's what happens when helium, which makes the weakest bond because it only has 2 electrons. It's a tie with hydrogen. H2 has 2 as well, okay? But helium has the weakest bond, and that's how it forms, okay? It's an induced dipole-dipole interaction. That's why I like the phrase induced dipole-dipole. It kind of tells you what happens. It's easy to remember that way. All right. So I talk about that, of course, in the in the packet there. Okay. It's kind of I'm kind of showing you. This is stolen from the book, of course, right? So I'm kind of showing you what happens in the book there. Okay. Now, have you been induced? Yes. You ever been to a baseball game where it kind of gets boring? So it's a Sox game. Cubs fan by marriage, right? If you go to a baseball game and it gets kind of boring and you're all sitting there in about the 6th inning and you're all kind of drunk and then someone decides, oh, okay, I'll do this. And they stand up and they do that, right? And the next person sitting next to them does that, right? And before you know it, there's a wave. So the wave is induced behavior, right? So because someone stands up next to you and does this, you feel compelled to do the same thing, and it just goes around the whole stadium, right? So that's an example of induction, and that happens, at sporting events all the time. Okay, sometimes you see it at the Cubs, but not usually, because the Cubs don't like to, show that. They think they're above being boring people, so they usually show something like a pigeon walking across the pitch. Okay, Northsiders. All right. Now, of course, you do see this in the World Cup occasionally, right? Okay. And you used to see it in British soccer too, before they changed the rules to make the win worth more than 2 points. Fans used to get bored and they used to kind of entertain themselves with like extreme violence, soccer violence. All right, never mind. Okay. Now, so simple question then. What property of an atom or a molecule determines if it can do induced dipole-dipole bonding? You saw it. Electrons, right? Okay. The fact that helium had 2 electrons, which were just for a second on one side of the atom, dipole was created momentarily, induced a dipole in its neighbor. Those 2 dipoles stuck. Okay. Now, if you think about it, the more electrons you have, the bigger this effect can actually be, right? So if I go back to my little picture down here, instead of having helium, I'm going to go with neon. Neon has 10 electrons, right? Let's pretend there's 2, 3, 4, 5, 6, 7 over there and only 3 over there. 7 minus 3 is 4, so that's a 4 minus, and that's a 4 plus. So that's a 4 times bigger dipole, all right? It'll induce the same 1, 2, 3, 4, 5, 6, 7 charge over here. 4 delta minus, 4 delta plus. It's kind of like throwing 4 ropes over rather than 1, right? Because there's 4 times the charge In the dipole, there's 4 times the strength of the bond. So that's the key thing, yeah? So we've done the same thing, but because there's more electrons in there, the effect can be magnified, if that makes sense, okay? So the bottom line is this. How can the degree of dipole-dipole bonding be increased? How can it get stronger? More electrons. Number of electrons is proportional to the strength of the dipole, right? And the strength of the dipole is proportional to the strength of the intermolecular force, right? The bond between the particles, right? The induced dipole-dipole bond strength. Okay. Okay, so that's, in a nutshell, induced dipole-dipole bonding, right? Okay, and it's kind of summarized right here. Okay, so the strength of an induced dipole, dipole bond is proportional to the number of electrons the atom has, right? The more electrons it has, the bigger the dipole it can induce just through random electron motion, okay? And we'll see that kind of concept as we go forward, all right? Now, this is where it gets weird, right? Because if you think about it, for every electron an atom has, it has 1 proton, right? And that means it gets heavier, yeah? So the heavier an atom is, the more protons it has, therefore the more electrons it has, therefore the more induced dipole-dipole bonding it does, therefore the higher its bond strength. And if you think about it, it costs energy to snap those bonds, right? So the stronger the bond, the higher the boiling point or the melting point. And what you'll see in the book is this rather annoying relationship, right? It says molecular mass is proportional to boiling point. If the only kind of bonding going on is induced dipole-dipole bonding, this is true, right? Molecular weight is proportional to boiling point. But then you think, oh, it's heavier, so it's got a higher boiling point. No, it's not because it's heavier, it's because it's got more electrons. Because it's got more electrons, it has stronger induced dipole-dipole forces, right? Because it induces a bigger dipole, right? So I like to say number of electrons is proportional to bond strength, right? But hey, the number of electrons is proportional to molecular weight. Bond strength is proportional to boiling point. Fair enough. And so that's what we see, because we can easily just look at a formula, get its molecular weight, and we can easily measure. These are macroscopic things, right? We can look at its formula, look at its molecular weight, and then just look at its boiling point up, right? Okay. And that's what you see, right? So in the book, oh yeah, it's in the data sheet. So here are the noble gases: helium, neon, argon, krypton, right? Yeah, look. The boiling point scales with the number of electrons. As the number of electrons goes up, so does the boiling point, because the strength of the dipole goes up, right? But because the number of electrons goes up, so does the number of protons, so the weight goes up. So yeah, molecular weight is proportional to boiling point, but that's not the reason, right? It's a consequence, if that makes sense. Okay, now, it's got a minute or 2 left. Okay, I think I'll just pause here and come back. Okay, we're going to talk, this is 99% of the time. 99% of the time, it's molecular weight versus boiling point. But we understand the underlying reason is number of electrons creating a bigger dipole, right? More electrons, bigger dipole, bigger bond strength, intermolecular force. All right, so pause there, come back in a second. Okay, so I mentioned 99% of the time, if it's only induced dipole-dipole bonding, yeah, molecular weight is proportional to boiling point. Under the hood, number of electrons is proportional to induced dipole strength, but it's the same trend, right? Okay, what about the other 1%? The other 1% features molecules of the same, or approximately the same mass, but different shape, okay? So here we have C5H12 in a linear form, we call that pentane, and then in kind of a globular form, that's kind of its tradition, that's kind of its systematic name, we call that isopentane, right? So we've got the round one versus the long thin one, okay? Turns out the long thin one has a slightly higher boiling point than the round globular one, even though they have exactly the same mass and exactly the same number of electrons and exactly the same general formula, right? C5H12, okay? So why would the long thin one have a higher boiling point than the round one? Because higher boiling point means stronger intermolecular forces. So, why would a long thin molecule have stronger intermolecular forces than the round one? All comes down to surface area, right? And here's an analogy, right? If you've ever been down a Navy pier, Yeah, how do you see the ships, right? When they line up at the dock, how do they line up? They line up like this, or do they line up like that? Okay, they line up long ways against the shore, don't they? Rather than, stern in or something, right? Why is that? Because that's a stronger bond to the shore. They're not going to get washed away in a storm, right? Okay. Why? Because when you're having a higher surface area in contact, you can kind of bond in multiple spots. Interesting. So when I have two long thin molecules side by side, I can induce a dipole here. I can induce a dipole here. I can induce a dipole here. I can throw 3 ropes across between 2 long thin molecules rather than just the one here. Okay, so if the only difference between 2 molecules is shape, the one with the higher surface area, and that's what it's about, will have a higher boiling point because it can bond more strongly, maybe with 3 little bonds rather than 1 little bond. Okay, all right. Fair enough. Now, next one. So we've done induced dipole-dipole bonding. That was first on our checklist. Everything can do it, right? Everything can do it. All right. What about that dipole-dipole force, right? So it's similar, but the dipole-dipole force is permanent. Remember, the induced dipole was kind of this time-dependent thing, right? Okay. Here, it's permanent. So some lucky molecules, as we already saw with HCl, have a permanent dipole, right? So if there's a picture right here, right? So here's HCl, right? Here's H, here's Cl, yeah. That end of the molecule, as indicated, is a little bit minus because that's a polar covalent bond, right? Okay, so this molecule is permanently a little bit minus on the chlorine end and permanently a little bit plus on the H end, right? Now, if I got a bunch of those molecules in a jar together, think about it, right? Here's its neighbor, all right? Now, it's going to sound a bit weird, but I call this the dogs in the park bond. That's going to help you remember, hopefully, right? If you own a dog, you know this. How do dogs greet each other at the park? Well, the north end of one dog is attracted to the south end of another dog, right? Okay, so, think of these like little dogs, right? There you go, right? So the plus end of this dipole is attracted to the minus end of this dipole, and they form these long chains, right? Now that's kind of like a chain of spaghetti, yeah? So think about a chain of spaghetti. Can you ever, with a fork, get into a big bowl of spaghetti and pull out one strand? No, because they're all tangled up, right? So these long chains form, they tangle up, and then everything stuck to everything else is now a liquid, okay? So that only forms, and it's a permanent dipole-dipole bond, right? Rather than an induced, right? This will also do induced, right? Because it's got electrons, but on top, so on top of that, it will have another bond, a stronger bond actually, a permanent dipole-dipole attraction, okay? So a similar kind of mechanism, it's a similar kind of delta minus delta plus attraction, but it's permanent, not induced, okay? All right, now, there's some analogies here, right? Because, and you guys are now expert at this because when you've completed that last lab with the molecular models, you can easily tell if a molecule has a dipole or not, right? Based on symmetry and the presence of polar covalent bonds, right? So here I got this molecule, right? So this one here is, if I draw it out, so that one is somewhat symmetric and the dipole goes through the middle, right? So there it is, right? So this one has a plus and a minus end. It will do just the same as HCl, but the strength of the bond, just like we saw with helium and neon, right? The bigger the dipole, the stronger the bond, right? And we can measure the strength of that dipole, right? Before we just talked about differences in electronegativity. Sure, if it's just a simple molecule, just one bond in the molecule, HCl versus HI, for example, right? HCl is going to have a stronger dipole, right? Because it's got a bigger difference in electronegativity between the atoms, yeah, okay? But same rules apply. The stronger that dipole is, the stronger the bond between the particles, the higher the boiling point. Okay, because it takes more energy to snap that bond, right? Snapping the bond is when it boils, right? Okay. Now, if we look at this table, all right, if you look at this table, I've purposely chosen things that weigh all about the same, right? If they weigh the same, hint, hint, same amount of induced dipole-dipole bonding, right? Okay, same number of electrons, more or less, right? But how they differ is their dipole moment, right? Propane only has CH bonds. If you look at the electronegativity of C and H, very similar, right? So it's essentially non-polar bond, right? Dipole moment's tiny, yeah? Okay, so there's no dipole. And then I go down the list here, I've got CO, that's that bond. I got C double bond O, I got C double bond O in a different environment, and then I got CN there. All right, okay. Now, as you go down the list there, those bonds get progressively more polar, yeah, as measured by the dipole moment, right? Okay, so the dipole, the charge separation gets greater, right? That's the biggest separation of charge, that's the least, yeah, okay? So on top of that induced dipole-dipole bonding, which is the same in each case because they all weigh the same, we have this kind of now additional bonding, permanent dipole-dipole bonding. This will be the strongest, this will be the weakest. How does that play out with boiling points? You guessed it, right? The thing with the highest dipole moment has the highest boiling point because it has the highest amount of extra bonding. Okay, so given a table like that, given a table of things of similar mass, different dipoles, thing with the highest dipole will have the highest boiling point, strongest intermolecular force. Okay. Oh, last one, right? Okay, just make sure I'm catching up correctly here, right? Hydrogen bonding. Now, hydrogen bonding, as I mentioned at the start, to a chemist is just a really strong dipole-dipole bond, but to an organic chemist or a biologist, it's a special kind of bond, right? Because they're super strong, all right? So, kind of said it here, hydrogen bonding is a special form of very strong dipole-dipole interaction, and they are the strongest intermolecular force by far, right? They're on the order of magnitude as a regular covalent bond, about a tenth of the strength of a regular bond, which is really high. Now, as suggested by the name, hydrogen's got to be involved, right? Okay, and let's see how it works. So we have the so-called hydrogen bond coordinate, right? So we have R, when you do organic chemistry, R stands for the rest of the molecule. R will probably be a carbon atom, right? And then attached at the end of the molecule is something very electronegative, right? Okay, and think about the three most electronegative atoms in nature. Fluorine, oxygen, nitrogen, right? Okay, it's not going to be fluorine in an organic system because it only makes the one bond, but if we did look, for example, at HF, we could do it, right? Okay, so I'll put oxygen, nitrogen, and maybe fluorine in brackets. That works for academic examples, but there's no fluorine really in nature, right? So all your chemistry in your body is not really involving molecules of fluorine, right? But they do have lots of oxygen and nitrogen, right? Okay, so that's oxygen, nitrogen, or in some weird examples, fluorine academic only, right? Okay, and if you like, that's one molecule, yeah? Will it hydrogen bond to another molecule? Well, we had to have a hydrogen atom, hence hydrogen bond, then, as shown up here, stuck to another electronegative atom, and then off to the rest of the molecule, right? So, molecule 1, molecule 2, that has to be electronegative, so that's O or N in natural systems, and F may be in an academic example. So the three most electronegative atoms, in practical terms, just either oxygen or nitrogen, right? Now think about that, right? Think about that. Think about where electrons go to and from, right? So if I have on this first molecule something super electronegative with carbon, the electrons are pulled that way a little bit. Just from differences in electronegativity, I create a dipole. If you think about it, I'm adding electron density into this X here, so I'm kind of reinforcing that lone pair on the back, which is important, right? I kind of made a kind of really negative lone pair there, okay? On this one, that's minus, that's going to be plus. The electrons are pulled this way from hydrogen, so it's, if you like, it's removing electron density from hydrogen. It's kind of exposing this back face and making it more plus, if that makes sense, right? So what do we have? We have X looking at hydrogen across this gap, and between them is a pair of electrons. Now, it's all the way over there, and this gap is too big to be a regular covalent bond by far. It's 3 times too big, right? But organic chemists and biologists love to say it's a weak covalent bond because technically there's a shared pair of electrons between these two atoms. That's not how chemists think, right? The gap's too big to be a covalent bond. It's just a strong, strong, strong plus minus dipole-dipole interaction. So if you think about it, this is the minus end and that's the plus end of the dipole, right? Okay. All right. So if you think about it, if I have Oxygen and nitrogen as possibilities over here in natural systems. Oxygen and nitrogen as possibilities over here in natural systems. There are actually 4 combinations that work. I can have, and here's 3 of them, right? I can have oxygen here, hydrogen, nitrogen, right? Oxygen, hydrogen, oxygen, or nitrogen, hydrogen, nitrogen. Which one did I miss? It was O, H, N, right? That's the one they missed. Yeah, so there's 4 possibilities. 4 possibilities, yeah. So wherever you see that hydrogen bond coordinate, O or N on one molecule, H and N or O on the other, hydrogen bond coordinate can exist. You'll get a super strong interaction. All right, now, examples. Obviously water. Water is awesome, right? Why is water so awesome? Well, think about it. What does water weigh? It weighs 18 grams per mole, right? What does neon weigh? 20 grams per mole. Neon boiled at 20 Kelvin. Wait a minute. So neon and water weigh about the same, so that's the same amount of induced dipole-dipole bonding, but water boils at 100 degrees C or 373 Kelvin, and neon boils at 20 Kelvin. What's going on? Well, it turns out hydrogen bonding happens twice for every water molecule. Look at it. Water has 2 OHs and 2 lone pairs, so it can go off and hydrogen bond twice, right? And when I show you those water molecules in those hexagons, each water molecule is hydrogen bonding twice. Awesome, right? Okay, so I got 2 of the strongest forms of intermolecular force in nature stuck on a small molecule. It's got a really immense boiling point for its weight. Okay, so water should have boiled at 20 Kelvin. It boils at 373. Okay, so water's liquid at room temperature because those bonds are so strong, right? Okay, nitrogen and hydrogen makes ammonia, right? Now, ammonia only has the 1 lone pair and 3 H's stuck to N, so it can only hydrogen bond once. Okay, so it's a gas at room temperature. Those bonds have broken in the liquid at a lower temperature. Okay, why does ethanol dissolve in water, right? That's called vodka, right? So it turns out, here's a picture of an alcohol molecule, right? Alcohols always have the COH group on them. Okay, that COH can go off to form a hydrogen bond. Okay, so anything with an OH or an NH in it, that's an organic molecule, can hydrogen bond to water. So that's why so many things dissolve in water, because they have O's and N's inside them, which will hydrogen bond with water, and it will dissolve, right? It will dissolve via hydrogen bonding, all right? Okay. Now the last one, I won't dwell on it too much, okay? But you may have heard of DNA base pairs, right? Adenine, thymine, cytosine, guanine, right? Watson and Crick, right? Okay, so when you have that double helix, so imagine this is like, you know, one of the strands of the double helix, this is the other, and there's a gap, right, and they're bonded across there. It's because they have complementary base pairs on the 2 separate strands, right? Okay, so those 2 strands line up perfectly next to each other because, now here's an analogy, right? So get a glove, get your most comfortable leather glove, right? And then before you put your most comfortable leather glove on, put a tip of crazy glue on the tip of each finger, then put your glove on. Is that glove ever coming off? No, because you form 3 really strong bonds and you've got a perfect fit, right? It's exactly what happens with these complementary, hence word complementary, base pairs in DNA, yeah? So cytosine and guanine form 3 perfectly lined up hydrogen bonds, strong bond. They're never going to come apart, right, unless we want them to, so there's never going to be any errors in replication. Okay, so that's very, very important. Here, not quite as strong, but adenine and thymine have 2 perfectly fitting hydrogen bonds across the gap, those 2, right? So these, you know, if you know anything about DNA, you know, the DNA sequence ATCG, right, that's your DNA sequence. That's just these things in a line, yeah? And then when you replicate DNA, you make, I'm getting into unfamiliar territory. I think it's called tRNA or something. So the other one codes for it, right? And when it codes, it doesn't want to make a mistake. Errors in DNA cause big issues, right? So mistakes are hardly ever made through billions of replications. Okay. All right. So hydrogen bonds are at the heart of DNA structure. They allow us to have vodka, and I mean water is liquid at room temperature. So all these powerful, powerful things are dependent on hydrogen bonds. All right, now there's only really one hydrogen bond question, okay? If you ever see water, HF, or ammonia. HF's the kind of academic example. Hydrogen fluoride can hydrogen bond, right? Because it's got HF with another HF, right? So so F, let's do that hydrogen bond coordinate. So I can have that, right? I can have that, right? That is the hydrogen bond coordinate, but it only really happens in HF, yeah, so it's like an academic example. But if I look at column 7, 6, and 5, and the hydrogen compound of the elements in those columns, right? Okay. If I look at column 4, if I get my periodic table quick, column 4, carbon, silicon, germanium, etc., right? If I just turn those into CH4, SiH4, GeH4, right? Okay. Well, carbon doesn't hydrogen bond, so it's the lightest. Methane is a gas at room temperature. As things get heavier, their boiling points get greater. As we would expect in the trend, that's just pure induced dipole-dipole bonding, right? And that's the trend we see for all of the columns and their lower members, right? But remember what I said about water? Water should boil down here at like 20 Kelvin, right? Because that's where neon boils, right? But look, it boils way up here at 373 Kelvin. So it should be here, but it's all the way up here. Why? Because it does hydrogen bonding. Bottom line is, anything that hydrogen bonds will completely blow its boiling point out of the water, right? Hydrogen bond, hundreds of times stronger than induced dipole-dipole for things of the same weight, okay? So you may be asked to put things in order of increased boiling point. If H2O, HF, or NH3 is in there, it's going to be the one with the highest boiling point, okay? All right. Now, so water's kind of amazing, as I mentioned, okay? And we already mentioned why the boiling point of water is so high, because it makes 2 hydrogen bonds per molecule. If it didn't do that, it would form a gas at 20 Kelvin, and the Earth would just be one solid ball of ice, wouldn't it? Right? Okay. All right. So no good. Is that right? No, that temperature. Yeah, there will be no liquid water on a planet like this. At this temperature, everything would be evaporated at 20 Kelvin. So no liquid water, no life. That's what I'm trying to say. Okay. Now, last couple of pages here, right? There's an old phrase in chemistry, and it's this one: like dissolves in like, right? So if I have similar molecular coordinates on 2 different molecules, they're probably dissolving each other, right? So hydrogen bond coordinate needs, heteroatoms on molecules, oxygens, nitrogens, right? So we saw that already, yeah? Now, you may be asking yourself a question, well, why does table salt dissolve in water while olive oil doesn't, right? So you've seen this in your house, right? So table salt dissolves in water, and that's called an iron dipole bond. We've already seen my favorite slide with the tractors, yeah? So because water has a dipole, it's like a whole charge and a partial charge sticking electrostatically, right? So water, the polar solvent, dissolves ions really well, right? Water, the hydrogen bonding solvent, dissolves things like alcohol with OH groups really well. So water dissolves almost everything because they can either hydrogen bond to it if they got the hydrogen bond coordinate component, or if they're in some way charged, polar or point charges, ions, right? So we have dipole-dipole bonding with water, we have dipole-ion bonding with water, and we have hydrogen bonding, which is really a strong dipole-dipole. All right. Now, down here, why doesn't olive oil dissolve in water? You've seen salad dressing, right? So, you've seen the vinaigrette dressing, right? The oil's on top, the water, the vinegar's underneath. Why does that go like that? Because the water sticks to itself more strongly than it would the oil, right? So in the oil, which is just a non-polar molecule, all it does is induce dipole-dipole bonding with itself, right? It will try to induce dipole-dipole bonding with water, but hey, water is so hooked up with itself in terms of hydrogen bonding. That's why water has a surface tension. If you think about it, water has a surface tension, right? Because all the molecules are kind of so strongly hydrogen bonded to each other, they don't stick to anything else. That's why water forms drops, not big. If you ever put a drop of acetone or nail polish remover on the counter, it spreads out real thin, right? That's because there's less strong intermolecular forces. Water beads as little drops because they're all kind of stuck to each other and they make the lower surface area. All right. So bottom line is, a polar material and a non-polar material, oil and water, will not mix because the bonds here are stronger between water molecules than between water and oil. Okay, and also the bonds between oil molecules, believe it or not, are stronger than between oil and water, just based on the size of the molecules, how many ropes I can throw across. Okay, so oil and water doesn't mix. That's why sugar does not dissolve in gasoline, right? You ever see these kind of, you know, Judge Judy cases where somebody sugars someone's gas tank, yeah? So if you put some sugar, don't do this. If you put sugar in your scorn lover's gas tank, it blocks up the fuel pipe, right? Because gasoline is essentially non-polar, right? Okay, gasoline's non-polar, sugar is hydrogen bonding. Sugar dissolves in water really well, just like alcohol, because it has OH groups, right? So it doesn't dissolve in gasoline, dissolves really well in water. And because it doesn't dissolve, it clogs up the gas line. So if you ever wondered why sugar in a gas tank's a bad thing, it's because of like dissolves in like, really. Or in that case, like doesn't dissolve in not like. Right. All right, so summary. All materials have induced dipole-dipole bonding. It's entry level and it's proportional to the number of electrons the atom has. In the book it says molecular weight is proportional to boiling point, but that's really under the hood. Number of electrons is proportional to induced dipole-dipole strength. It's really the induced dipole-dipole strength which leads to a strong intermolecular force. More strength to break it, higher boiling point. Additional molecules, HCl, great example, have that additional amount of permanent dipole-dipole bonding because of the net dipole in a molecule, okay, and we've looked at different molecules now with net dipoles, right? And then if you see the hydrogen bond coordinate, it just blows everything else out of the water. It's much, much, much stronger. That's, if you think about it, that's why nature makes us from carbon, oxygen, and nitrogen. Literally all organic molecules are carbon, hydrogen, oxygen, and nitrogen, right? Why? Because that means they can hydrogen bond. We can make cells, we can make DNA, we can make all these interesting things. Okay, so hydrogen bond's strongest, followed by dipole-dipole, followed by London dispersion. And then remember, just the classic chemist phrase, like dissolves in like. So things which have dipoles or kind of, if you like, point charges like ions will dissolve in one another, right? Because it's plus attracts minus. Things without dipoles, non-polar molecules like hydrocarbons, like carbon and hydrogen only, right? Very similar electronegativity between carbon and hydrogen, therefore no net dipoles. They only do induce dipole-dipole bonding. We call those dispersion forces, London dispersion or induced dipole-dipole. So, you know, different oils will dissolve in each other, right? A very kind of neat little cooking trick, because butter is basically an oil, right? That's solid. And olive oil is an oil, which is liquid. So they have different melting points, right? And people, and my friend, I just say a physicist in our department, no names, right? So I'm having a real time. Is there any way to kind of get my butter to melt more quickly? And I go, yes, Andy, there's a clue. Get some olive oil, put it in your pan, and then put the knob of butter on the olive oil. And the butter will dissolve in the olive oil because like dissolves in like. Try it, right? If you want to try and melt some butter, but not melting it, dissolving it, right? Put some butter in the pan with some olive oil and it'll dissolve in. Okay, you don't have to heat it, okay? Might take a while, but it works. Like dissolves in like, practical application. So that's olive oil and butter maybe, right? Okay. Then we have acetone and chloroform. These are molecules with permanent dipoles. And dry cleaning fluid actually is a molecule with a permanent dipole. Oh, extra credit. Dry cleaning fluid. Dry cleaning fluid, just get me the formula, right? Okay. Dry cleaning fluid is called dry cleaning because water dissolves dirt, right? And dirt can be ionic, right? Or polar, right? So water dissolves off, and hydrogen bond, right? So water dissolves off a bunch of stuff just by bonding to it and taking it away down the drain. But if you can't use water as a solvent, you use something else, hence dry cleaning. But that something else, that other solvent must have a strong dipole, like water, okay? So find the molecule they use in the dry cleaners that has a strong dipole. That's the solvent used instead of water, so it's dry cleaning. All right, and that's going to be due on Thursday. Okay. Finally, hydrogen bonding and ion dipole bonding. We saw this. So ethanol dissolves in water, sugar dissolves in water because of hydrogen bonding, and water dissolves salt, table salt for example, because of charge dipole interactions. We saw that with my favorite slide with the tractors and trailers. Okay, so stop there, just about out of time. That's our last packet. Please try and get this done by Thursday. If you've made it to the end of this packet by Thursday, stay tuned for 5 more seconds. See you next time.
High five! Great!
Hi everyone, here's something fun. So occasionally I like to give you a surprise extra credit. So if you're watching this, okay, congratulations, you have hopefully reached the end of the last video, okay, and here's my happy smiling face, right? If you're here and you're watching this before the deadline for watching this video, send me an email immediately with the line in the title, give me 5, right? Give me 5 points of extra credit. I'm giving you 5 points of extra credit for getting to this video on time. Woohoo! Okay, see you next time.
High five!